Right, so let's look at how we can use titrations in a certain manner to determine percentage purities of samples, or maybe determine the percentage of a certain species. So, for example, a certain amount of iron in an ore, or in the example that we will be looking at, is we have a substance that we know has been contaminated with lead, or at least suspected. And then we perform an experiment to determine is it indeed contaminated with lead, and to what extent is it contaminated with lead. Um, so, how can we use the ideas of solution as reacting with one another to give us some precipitate, and then from that, how can we then determine the percentage purity of the sample that we started out with? Right. So if we read this example, we're told a sample of ammonium nitrate to be used as fertilizer is suspected of being contaminated with lead nitrate. Okay. A 1.5 gram of this sample is then crushed, dissolved in water, and treated with potassium chromate to give a precipitate of 0.569 gram of lead chromate. And we need to determine the percentage purity of that initial samples. In other words, what part is contaminated with lead and what is actually the ammonium nitrate fertilizer. So I like to start with drawing a qualitative picture just to get our mind ready. So essentially what we have is we have some sort of sample, and this sample is divided into two pieces, not exactly, linearly two pieces, but we can think of it as such. So the one part of the sample is the ammonium nitrate. So that is NH4NO3, right? Is the red part. And that makes up a specific percentage of the sample. The other part is the contaminants. In other words, that should be our lead nitrate. And that also makes up a certain percentage of what we're looking at, right? So that's a sample that we have. And this sample is then crushed up and we put it in water. So we then say, all right, so we put that into a beaker of water, and what do we have then? Well, we have the ammonium nitrate and we have the lead nitrate. They will separate. Salts of nitrate are soluble, so we have all our species in here. And to this beaker, we then add, so let's say in another beaker, we then add some potassium chromate. So potassium chromate, CrO4, is in here. And this one contains lead nitrate and the ammonium nitrate. Right. And what we do is we add the one to the other. So we add that in there. We're not told what the amount is, but we're told some other information that will be useful. And then what happens once the chromate solution is added, we end up with a solution that has potassium, there's nitrates, there's ammonia in it, but the chromate binds with the lead. So lead chromate, incidentally, is a yellow substance. So then a precipitate falls out of solution. And we assume from the question that enough potassium chromate is added so they can keep on adding potassium chromate. They know how much or at least they know that they've added enough so that there's no longer any precipitate forming. So you add and you add and you add until there's no more precipitate that forms. So there's enough potassium chromate. That's the takeaway. So there's some solid that forms, and we're told that this solid has a mass of 0.569 gram. The other bit of information that we were given is that this sample, so the total weight of this sample is 1.500 gram. I just need to remember to move all my things up one step. Okay, so that's our image. That's what we need to have in our mind. So the question now is, what do we start with? What is the kind of information do we need? So what are we given? We're given the mass of something called lead chromate. So lead chromate is CrO4, and we know some solid of that forms. So information that we're given. So how can we relate the fact that we've added potassium chromate to this mixture and then we got lead chromate out from that? Well, it's an exchange reaction of some sort that must have taken place here. So we will have our lead nitrate, so the species of interest in the sample, and that is being dissolved. So we're told we dissolve the sample, so we know that's dissolved, and salts of nitrates are generally soluble. We then, to that, add potassium chromate, which is also soluble. We're told the solution of that. And that then reacts to give something. So it's an exchange reaction, right? So the exchange reaction tells us that the ions swap. So we can say the lead goes there and the potassium goes there. So lead chromate, we know, forms PbCrO4, and that is the solid that forms. The other thing that forms is potassium nitrate, so potassium NO3. But we know there are two nitrates and two potassiums, so in other words, there needs to be a 2 there to balance. Okay, notice how I did not write K2NO3, for example, is potassium has a +1 charge and nitrate has a -1 charge, and you cannot change that fact. So what you write down is the base KNO3, and you need to then balance it from there on. Okay, so this is just our thoughts. So how would you write this properly in any examination? So you would start with to say something like, when the potassium chromate is added to the solution, containing lead nitrate, a precipitate forms by the following reaction, by the reaction equation below. Right, and then I'm going to cheat, and I'm going to take this thing, I'm going to move it there, because that's what you write then there. So then you say, right, now we have this information. Then your next step is, it is given that the mass of the lead chromate equals, what's that, 0.569. Gram. And we know we cannot relate grams to anything else, because what we want to do next is we have some information regarding the species here, right? So we have its mass. But what can we use the chemical equation for? We can use the chemical equation to relate the, let me just change that, to relate the number of mole that of this thing that forms to the number of mole of the thing that needs to react, right? And we have the mass of this thing that forms. So hence we can get the number of mole and then we can relate it back to the mass of the NO3. Once we have the mass of the NO3, we can determine what percentage it made up of the original solution or the original sample. So it is given that that is, so then you can say something like, this implies that the number of mole of the lead chromate will be equal to, of course, the mass divided by the molar mass. So you take, let me just get my papers here. So that is then equal to mass of lead chromate divided by the molar mass of lead chromate. And you should, so in other words, you plug in here 0.569 gram. The molar mass of lead chromate is 323.192 192 gram per mole. In other words, the gram cancels, the mole goes on top. You should get a value of 1.760 and a bunch of numbers times 10 to the negative 3 mole. Right. Now the rest of the argument comes in. If we know the number of moles of lead chromate, then we can relate it using our chemical equation to how many moles of lead nitrate there had to be in the original sample or original solution. So then because lead nitrate is in a 1-to-1 ratio with lead chromate, it implies, or therefore, the number of moles of lead nitrate must be equal to the number of moles of lead chromate. Right, so you use what you're thinking, you need to put that into words. And that's quite an important thing. So, I mean, you can then write here, it's 1.76 times 10 to the negative 3 mole. If you want to, I don't think you need to write that unless you want to have, just for your own sake, you want to be explicit. Okay, so then once we have the number of mole of a species, then we can always calculate its mass. So I think for this step, you can just say, therefore, the mass of lead nitrate is then equal to the number of moles of lead nitrate times the molar mass of lead nitrate so it's equal to this 1.76 times 10 to the negative 3, sorry, there's dots there, mole times the molar mass of lead nitrate, which is 331.214 gram per mole. And this will give you a value of 0.583, etc. gram. So now I know how much lead nitrate, what was the mass of the lead nitrate present in the solution, the total number of lead nitrate. So from there, we can then calculate the mass percentage of lead nitrate in the sample. So therefore, the mass percentage lead nitrate in the sample is, so then I'm just going to say mass percentage lead nitrate is equal to the mass, so 0.583 gram lead nitrate divided by 1.500 gram sample, and then we multiply that, of course, by 100%. We should get here an intermittent value of 38.8%. And why is that not our final answer yet? Well, because we're asked determine the percentage purity of the sample. In other words, we're not interested in how much lead there actually is. We're just interested in how much ammonia nitrate there actually is. So they can write again, therefore, the percentage purity is equal to 100% minus 38.8%, which is equal to 61.1%. Three significant figures. Why? We're given three significant figures. So 1.500 is 4, but 0.569 is three significant figures. So there we go. That is what it is. So essentially, you can always, a nice way or good way to figure it out for yourself is writing it backwards. So you say you want the percentage purity. How do you get that? Well, you actually need the percentage impurities, and that is the mass percentage of whatever your contaminant is. So to get that, you need the mass of your thing. To get the mass of anything in chemistry, you usually need to work out the number of mole. And how can you get the number of mole? You use the reaction equation, and then you are given the mass of one of the species. So you always have the mass of one of the species. In other words, once you have the mass of one species, you can determine the number of mole of anything in the chemical equation, and then you can also determine the mass of anything in the chemical equation. So that's actually the most important point, is the fact that you use the balanced chemical equation to do what you want to do. Because once you have that, you can relate masses, you can relate moles, you can even relate atoms. So the percentage atoms of something, anything like that. So you'll always be given information about one thing, then you deconstruct the chemical equation and you balance it. And once you have it balanced, you can relate anything. Okay. Additionally, I mean, you saw I wrote a bit more information and tried to dictate the logic. You could write even more if you want to. You can then say, once we have the number of moles, we can use the molar mass to calculate the mass. Therefore, the mass is da 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 da. To calculate the mass percentage, we will use the mass of the impurity divided by the mass of the sample, and then you calculate it. So that the person, whoever's looking at this, can also follow your logic, your train of thought. It doesn't help that you're just writing stuff, especially when it comes to the mole ratio, because you need to say, because this is in a one-to-one relationship with lead chromate, then you look at how the number of moles relates. Of course, if it's not one-to-one, then you scale a factor here. So then there will be some factor that is related to 2/1 or 3/5 or whatever it needs to be. But you figure that out from your mole ratio. Okay, right. So I'll see you in the next video. Thank you for watching.